So for this very last topic here, I just want to recall something with you together. A geometric sequence, or in this case we're talking about a series, and remember the difference. A sequence is just the list of numbers that grow in a geometric way. And remember that means we're multiplying by the same thing each time as you go to each new term. So in this case that factor is r, right? So if my first term is a, then I multiply by r, but then I multiply by r again, and then again, etc. And the geometric series just means this just goes on forever, adding all the terms together. Now, if that r value is bigger than 1, where each term is growing larger and larger, so if you add all the terms infinitely forever, it's just going to grow to infinity. It's going to get completely large forever and unbounded, we say. However, if your r is less than or equal to 1, in fact, actually, it should be less than 1, not equal to. If your r is less than 1, and actually it's absolute value, technically speaking, because you can kind of have this back and forth thing, then we say that it converges. And remember what that means is, if you add all those infinitely, eventually it's going to get to like a plateau or a maximum that it could reach. Okay? A classic example of this would be, imagine we have a bouncy ball that can bounce infinitely and never stop. And if you throw this bouncy ball off of a 100-foot building or something like that, let's say, then it's going to bounce, and then it's going to bounce again, and it's going to bounce again, except actually it needs to decrease in height over time. But let's just say it actually does this, and it can go forever, right? If I were to give a number to this and say, okay, well, let's say it reaches 60% of its original height every new bounce, right? Do you agree that 60% does fall into this category of being less than 1, because as a decimal, that's 0.6. So what we're saying is, if I were to add, if I was trying to track the ball's height, let's say, total height over time, so right here, its total height is 100 feet, but then here its total height is 60% of that, and then 60% of that, and 60% of that. It's going to just continue bouncing, this magical bouncy ball, but then eventually it's going to be so minuscule that it's barely gaining anything, and it's going to approach, well, we've learned about asymptotes, but it's kind of horizontal. If we were to keep track of the total height, it's going to get closer and closer to a certain value, but it's going to kind of plateau. And this idea of it ever increasing but getting closer and closer and closer to one specific number is the idea of converging. So there's a really cool thing that relates to trig functions that also relates to calculus. We're kind of looking ahead here, and it's totally okay if you're not completely grabbing onto everything for this particular example. Don't worry too much about it, okay? Let's apply this to a series that involves sine. So let's go ahead and look at 1 plus sine squared x plus sine to the 4th x plus sine to the 6th x plus etc., etc., etc. We can see that this is geometric because from one term to the next we are multiplying by the same thing to get each new term, right? In this case we're multiplying by sine squared, and then we're multiplying by sine squared again and by sine squared again. And this thing just adds forever infinitely. Now the cool thing is, we can guarantee that this r value, right, in our case r equals sine squared x. We already know that sine x by itself has this property, right? It's bounded between -1 and 1. But sine squared, if you square any of those numbers, it's still going to be within that range, actually. It's just kind of how it works. So the other nice thing about this is that this is always positive, so we're not letting the negatives in here, because that becomes kind of weird. And in fact, for now, it's really even fine just to leave that as r less than 1, actually. But the cool thing is I just want to show you that if we add this infinite sum up, it actually converges, it reaches a plateau, and based on this formula we've learned in the past for convergence, here's what it converges to. Well, a represents our first term, which is 1, okay, so we can identify a equals 1. So if it converges to a over 1 minus r, it converges to then 1 over 1 minus sine squared x. Now I want you to remember something here. There's another relationship we've learned recently, that Pythagorean relationship. Remember how sine squared plus cosine squared equals 1? What happens if I subtract the sine squared over? Sine squared plus cosine squared equals 1. Subtract the sine squared, you have cosine squared equals 1 minus sine squared. 1 minus sine squared is the same as cosine squared. So that equals 1 over cosine squared x, which is secant squared x. So this infinite sum right here, this is pretty crazy. This infinite sum right here that goes on forever, if you let it grow infinitely in that way, converges to secant squared x. We can basically say if we let this actually get to infinity, I know that's kind of weird to think about what it means, it becomes the same as secant squared x. Super crazy, right? So that's just a nice last little tidbit to go with this. Definitely extra, but interesting. And we'll see you next time.